Okay, we're on. Good afternoon. I'm Peter Larson from Loudsoft, and I want to give you a presentation. Could you switch on this projector? Okay. So I will be talking about the fine circle. And if you look up to the left, we have on the left side driver design programs, starting with fine motor. Let me see if I can point somewhere. Can you see the mouse? No, I will put it on here just a second. There's a marker. And that doesn't work either. I need to have the laser pointer. Here it is. Okay. Fine motor is the basic program that has been around for a number of years and now is kind of industry standard. It's used by many companies. Then we will talk about the newest edition, fine suspension, which can design all the suspensions, spider and surround. And then finally we will have a look at fine cone, which we've had for many years also, but now in a nice version which is easier to use. And on the right side we have the system design programs. First of all, FineBox, that started as a very simple program that you could have responses based on detailed small parameters. Now it can do a lot more, and I will show a little of that. Then we have fine crossover, and there's still a lot of people using passive crossovers, and fine crossover has some very neat features. And then fine DSP is the modern version of that for, let's say, general purpose DSP, because it produces coefficients that you can use in any DSP. And then finally we have the two measuring softwares or systems, Fine R&D, obviously for R&D work, and then Fine QC for quality control. They actually use the same hardware. So once you got the hardware, you can just buy the software package for the other. Okay, so what I'll do now, I'll go through a kind of project which is also, or will be an article in the Voice Coil magazine. And this is about a two-way design. 18-liter bass reflex box, a two-way, 6.5-inch woofer, 1-inch stone tweeter, and in frequency range specified from around 40 Hz up to 30 kilohertz. Very common. There's nothing special about that. What we will do, we will use all these softwares. We will start with FineBox because it will give us a general overview what is possible and also what is required. Because from FineBox you can derive parameters for designing a driver. So it works both ways. Then we will do basic analysis and cone optimization in fine cone. And when I say cone, I also mean the surround. People have a tendency to forget about the surround. No, the surround is very important and often neglected. So I will show a bit about that. Then we'll do fine motor design, and this, of course, is necessary to get those small parameters we have found was necessary. We can also optimize the LEX, the inductance of the voice coil in fine motor, and we will do some of that here. Then, of course, we will use fine suspension. What is interesting is that we already in fine cone simulate the surround and actually also the spider, say in a good way, but not necessarily at a high excursion. And that we will do with fine suspension. So we'll work with these two programs for the suspensions, the surround and spider. And then, of course, we will end up measuring everything with fine R&D. Fine R&D, I can speak a little about it when we come to it, but it's very powerful. It can contain up to 16 responses on the screen simultaneously. And what's especially interesting is that this software can measure in any room and take away the reflections from the room. So in a way, it's anechoic. And all the 16 responses are saved with the time response. That means that you can go back and select another time window, another smoothing, or whatever you want, but all the data are kept. So it's really versatile this way. Okay, so let's start. We say that we will use Findbox, and we will use it in the mode that's called inverse Findbox, because we're going to predict the parameters we need. And let me try with the mouse. So we say specify box volume of 18 liters and solve for volume. So that's our main parameter. We know nothing else so far. Then we go to the next screen and then select a driver. And since we don't know anything, we have a list of typical drivers here, and I have highlighted the 6.5 inch here, which we will select. As soon as we select that, we will get this table here that has required teal small parameters for getting a good response in 18 liters. So this is a condensed information that can help us to find, let's say, a good target. Here we have a number of curves, and we have a little time, so I'll try and go through. The first response, number 1, is brown here, and that's the upper curve. Show it with the mouse again, this curve there. And it's nice and flat and goes down to, say, something about 50, 55 hertz or something. Pretty good, but not good enough for the purpose we want. So therefore, we redo this again. I didn't show it, but we redo that inverse Findbox, and now solving for 40 hertz. And that is the blue response, if you can see it there. And from here to minus 3 dB is very close to 40 hertz. And that was our target. And for this target, we have these teal small parameters that are needed. So now we have found the target parameters for the woofer we're going to develop. And this is a nice starting point. Yeah, I'll mention also that there's another curve there. That's the red one. If you look at it, extends a little further down. It's because we have chosen another, let's say, tuning. Because if you put this speaker in a room not far from walls, you will have more bass, and therefore this response is trying to get a flat response in a room. And it's just, let's say, one way to do this. You can do that more if you measure real responses in the room. And even with fine R&D, you can decide how many of the room modes you want to include. Because with one measurement, they will all be there, and then you can find out. We can always talk more about that later. But anyway, we have made one curve for the room response. And if you look here, the red curve, this is woofer excursion, which goes very high at low frequencies, because now we are essentially in free air because the port is just an opening, and therefore the speaker cone moves very much. This is the excursion you see there, which is not good. With this, the red one, we automatically have limited that just with a higher resonance frequency. So we were always told that the resonance frequencies should be low. No. That's not always a good idea. I just mentioned it now because in speaker design 20, 30 years ago, there were rules that this is what you can do and this is what you cannot do. We don't use those rules anymore. We make simulations and find the best compromise. Okay, so let's go to fine cone. In fine cone, we have templates. And this is one template for a normal cone, what is it called? Linear cone. curvilinear is the name, which is straight here and then a radius there. And you can see all the dimensions on the sketch, and you just key in the numbers you want, and then this one will change according to the input. It's very powerful and very easy to use because engineers are really bad in making CAD files. And the CAD files must be perfect for this FEA simulation. So this is one way to create the CAD files without the CAD. You just put in the numbers. Okay, so this is our complete file. This is the meshed finite element model. There is only one place I have cheated. That's the dust cap. You can see the dust cap is very tall. We have a little time. I made a loudspeaker like this many years ago, before I had fine cone. And then with fine cone, when I got that, I analyzed it, found out that the dust cap was really bad. I have made a large dust cap, very flat, and that's not a good idea. You have to have it high to have stiffness in the vertical direction. So this is precisely what I did there. This was something I did from my experience. And if we have enough time, I can show you about it. I will not do it now. But we know a high dust cap is actually good and not large in diameter. Small and large is really good. So based on that geometry, we will get a simulation fine cone with default data. And these default data are actually quite good. They're taken from real speakers, so you get a meaningful response the first time, and it is here. So what we see here is on axis the black curve, and then 30 blue and 60 degrees off axis is the red one here. And when we look at that, we see it's not bad. There are some resonances there that we would like to avoid, but otherwise it's not too bad. And here you can see at the right the parameters for the cone. There are the coordinates and everything, but you can see that it has just used paper, normal paper or end paper from Kurt Miller, which is something you can buy today. Because we have lots of data in the database. The database is actually here, material data. There's a full database on lots of materials, and many of them are from Kurt Miller. So it's real data we have used. Anyway, let's take a look at this response in more detail and find out what is really happening at these two peaks, for example. So we go to this picture. And I don't know if you can read it, but you can see that there are two cone modes. And if we have extra time, I can animate this for you. But what happens is that basically that edge there, the cone edge and the surround edge, this cone edge is moving up and down. And it stays there. It's a resonance. It's a mechanical resonance. So that happens at, what is the frequency, 739 hertz, typical mid-range where this happens. And then we have the first real cone breakup mode here. This mode there is moving up and down when we simulate it, and this is happening on all speakers. It's the first real cone mode. Okay, so now we know what is happening and causing those peaks. Then, I don't have all the pictures, but anyway, this is the result after optimization. And you can see the black curve is what we have calculated, and the blue curve is the real speaker measured. And this is pretty close. It's a good prediction, and it shows the main thing, that it's well controlled and quite flat up till we have the peak. That is the cone mode at, say, 3.5 kilohertz. So this is a good simulation. So what did we do to make it this good? I don't know if I can see it anywhere. Let me see here. Okay. Those data, but okay, I don't have it written there. But the thickness of the surround here. So when we talk about the first mode where that cone edge and the surround is bending and resonating, what can we do about it? The first thing you will think is about strengthening the cone, make it stiffer. We can also have more mass there. Or we can change the surround, maybe change the shape or the thickness. And to spare you some time, I have tried both. And if we put on stiffness with the cone, which is not that easy, by the way, but it has a tendency just to move that resonance in frequency, maybe 200 hertz. It doesn't solve the problem. So instead, I have applied the old rule of balancing the masses of the voice coil, the cone, and the surround. If you think about the energy transfer between these three, if they have approximately the same mass, there will be no inconsistency. So that the energy flowing from one to the other will be, I call it even, but you know, there's not a weak point in having very little mass in one of these components and a high mass in the other. That's not balanced. That's one of the old rules, and it actually applies still today. So what did I do? I made the surround thicker. I made it 0.6 millimeter thick, which is much thicker than surrounds are normally. But it solved the problem. And it's something I have found out since, that it's very often neglected. The thickness of the surround can solve many problems. Later on, we will analyze this in fine suspension and optimize it. But now we have optimized the frequency response with this thick surround. I think we have time for questions. Otherwise, I'll come back to it. So this is the final model. Doesn't show us too much here. We just go on. So having optimized the cone, we go to fine motor, and time is running. With fine motor, we put in some basic dimensions for the cone area and so on, all of the other things than the motor itself. And then we say, okay, we want a DCR of 3 ohms in this case. And what can we do then? We say we start with a motor, a standard motor, an air gap, and then we have a wire table. Then we start from the beginning with the thinnest wire we have and wind a 3 ohm voice coil. And then we calculate the whole, all the parameters, and plot that on the curve, the red curve out there. And this curve has winding width on the axis, on the horizontal axis. So it goes up to 25 millimeters. The yellow area is indicating the top plate. And if we have a very short winding, say 1 millimeter, you can imagine that's a very short voice coil. That's underhung and not very effective, but it has great linearity. So those are underhung voice coils in the yellow sign, and as soon as we come to the right side, we have normal overhung coils. And therefore, this line represents about 50 different simulations, just one line. And we can select between them by the mouse, and every time we do this, all the parameters for the winding itself and for the small parameters are calculated as shown. So this we start with, and we can see that we don't have the linearity we'd like for the BL curve. It's pretty symmetric because we have extended the pole piece, and we can see how the flux lines are pretty symmetric about the gap. So this is not bad, but that BL is not high enough. So after some time, we find out that we could select or rather focus the field, the flux. I should use the mouse, by the way. So we focus the field by undercutting the top plate, undercut the pole plate, above the top plate and below the top plate. And there we get this very nice and flat BL curve. We have used a voice coil with a flat wire. It may not be easy to see, but it's 0.12 times 0.5 millimeter. So flat wire, flat copper wire. We can select different kinds of wires in the program, and we can have multi-layers and in and out and all that. But this is a simple coil with flat wire that works really well. Okay. Yeah. So that gives us what we wanted. I should say that in this case here, we had a step here, a bumped backplate to have enough excursion possibility. But then the latest one, we decided to use a thicker magnet, and therefore the bump was not necessary. Okay, finally, fine motor, we look at shorting rings because we have the red curve is LEX. This is plus and minus 6 millimeters there, yeah. So this is the LX curve, which the induction is very high when the voice coil is down the magnet system and low when it's above. That's very normal. It's not nice. It will produce some offset and gives nonlinearity. So now we have put in 2 rings. I'll try and make it short. 2 rings here, above the top plate and below. And in many years you have just put in a ring and say below the top plate. That will do the job. No, it has to be more precise than that. And this is why we have a lot of parameters we can control. We can control the thickness of these rings. We can control the material. Can be copper, can be aluminum. So there's a choice there. And of course, we want to have to suppress this high LEX there, but very often when you do that, then you get the opposite, that you get a maximum at the other end. So we want to balance it. So all in all, we have done this solution here, and you can see the green curve. I need to point here. The green curve there has much lower induction, and it's almost symmetric about the vertical line, center line. That is good because it will produce hardly any DC offset when the speaker is playing. And DC offset is our enemy. That creates intermodulation distortion, which Klippel rightly predicts is the worst you can get. It's a very horrible kind of distortion, which you don't hear really, but it's just making the music sound hard. So we really want to avoid that. Okay, let's go on. And now we get to the surround, and I have again modified the template at left here, half roll surround, and if you note the thickness of 0.6 millimeter, does it say yes? So that's what we predicted in fine cone, and this I have put in here, and starting with those dimensions we thought about, and then used a rubber from Kurt Müller again, and then we see the profile. When we do this, then this will roll up and down in steps. This is the nonlinear finite element engine we use here, so that we can get the KMX curve, which is the stiffness versus excursion, KMX. Actually, it's just called KX here, but anyway, it's the same thing. And we notice that it has this U shape with a more or less flat area in the bottom, and then it stiffens up when the excursion is high. This is actually attractive. I will tell more about that in a moment. But we can see that we have some unsymmetry, because this line is the mirrored curve, and if it's perfect symmetry, they will overlap, and they do not overlap. So we need to do something about it. So there's one parameter which especially will help us there. That is this offset here. And this we changed from 1 millimeter to 0.3 millimeter. So we can move this. If you move this further down, then of course you will get more excursion possibility upwards. So that's what we did. And now we get a perfect response, which is U-shaped and has a nice area there, the green area, and it's very symmetric. This green is defined by this IC number there, and it says that the operating range is with a stiffness within 75% of the nominal. So that's our working range, which is, say, a little like 5.5 millimeter plus or minus. Okay, so now we have optimized the surround. We can do the same thing with spider. And again, we start with a template and just put in dimensions. We start with the inside and outside dimension, and then we can vary this number. That's the width of each wave. And again, it will find out if this distance will actually work with a full wave, and therefore it will check your input that it's actually possible. So once we have done that, then we are seeing the movement up and down like before. The spider is working quite well. I should say that we'll need to limit this point here. And limiting means that we make it with the green line set ID, means that it's fixed following the voice coil. So there's a stiff connection to the voice coil, means stiff glue. On the outside, the red line, this is glued to the frame. So those are the two fixed points. Again, we can improve this by modifying the waves and especially the height. And then you can compensate for this non-linearity, which we have done there, and this one works perfect. That is the green line here. It looks like the other one here. It's maybe not perfect, but it's really good here in the working range. Now we have added the surround we designed before. That's the blue line. So this version will actually add the two, and then we have the total compliance or the total stiffness of the total suspension is the red and white line. That's very nice. I should say that this is quite normal that we have the surround being very soft compared to the, have the spider very soft compared to the surround. Is it a good idea? No. You have to balance it. And therefore, I showed another speaker in the beginning with a higher resonance where we try to balance this. I don't have that data now. But I have imported this curve here. That is the BLX curve we had in the beginning from Fine Motor. And in the green range, we are at minimum 82% of maximum BL. This is the requirement for Klippel to get low distortion. And that range should correspond roughly to what the suspension can do. And then we have done a balanced design where the compliance and the BLX curve, they have similar ranges. Right. And I think we are close, but we have more time. So I'll just continue 5 minutes, and then we'll say go over to Dynaberg. Okay. So since this was a two-way design, we will again use Finebox for the basic design, and then measure with Fine R&D. Then we'll do crossover design with Fine Crossover, which was let's say, the main idea to make this a passive system. But I was tempted to try the same thing with fine DSP, and I'll show an example of that. And then, of course, we'll make final measurements with fine R&D. So this is fine R&D. We have space for 16 measurements, and as I said before, each of them have all information with a phase and full frequency response. Then we decide for each one what time window should we have so that we can have an anechoic response displayed. But the full information is still there in each case. So there's a lot more you can derive from it. You can derive distortion and waterfall and phase and so on. So all the information is still there. Then we take these curves and drag them into the crossover. Maybe you can see that it says here, drop. So we can drag a curve there and drop it. Drag a curve from fine R&D and drop it here for each there. We have, I'll show that in a minute, but with this, we can optimize each section, have a filter. Here's a second order filter with a crossover frequency. It will calculate it running. We can just move it with the mouse and it will calculate the parameters of the crossover. And we can optimize slopes and crossover points and lots of things. So what we end up with is this response. The white response is 30 degrees off axis. That is what we prefer to optimize. When we have a speaker and look at, say, on-axis, in effect, it's only in one point the on-axis response is measured. But the off-axis response will spread into the room and gets reflected. So therefore, the off-axis response is actually more important. And this is why we choose to optimize the 30-degree response. But at the same time, the other responses are included. But we optimize the off-axis response in this case. And then we have the selection to optimize, and it says consider low impedance. Actually, we don't use this option here because, sorry, we do, because this is a passive crossover. And there we have to consider impedance. We do not want the impedance to drop to 1 ohm. Maybe the amplifier can stand it, but we're not sure. So for safety, we need to go above minimum. Okay, so this is the optimized response. Now, the green line is our target there. And we can see we are quite close. The blue line is the on-axis response, which is nice also, but rising a little here. The green line is actually sloping slightly downwards, which is seen on many good loudspeakers, that the off-axis response is sloping gently down. So this is normal. Okay, so we could say that this was our final design, but I have one addition here. And now we have actually improved the linearity here. And we did it with these circuits. Let me see. Yeah, here. We have some ALTI circuits. These are anti-resonance circuits. And this frequency, I should be able to see. Yeah, here. So now we can see, maybe it's not easy, but for this circuit, we have the resonance frequency, the bandwidth, and the level we can control independently. So we can simply tailor this cut in depth, frequency, and width. And this is a new addition we have made. It's so nice. And therefore, we have actually been able to make the curve you saw there. It's much closer to the target. Okay. Of course, if we did the same in the digital domain with DSP, we could do whatever we want. And here's an example of the same data. We have equalized the white line quite a bit more. It's really flat, and is especially flat here in from 1 to 3, 4K, which is the most important range because that's where the ear is most sensitive. So we really need to concentrate on that. And anything, for example, at a little peak at 2.5K of 1 dB, can we hear that? Yes. Everything above the level, the average level, can be heard because it's so critical, that range. So we really need to pay much attention to that. Okay, so this was the quick going through the fine circle with a two-way design, and we will talk about Dynaberg. So this is the Dynaberg passive driver. The real thing is here, and you can have a view afterwards. It's an active part in the middle. Show that. Need to put on this again. Yeah. So here in the middle we have the active part, the active driver, and then outside we have a part of a diaphragm with suspensions. So that is the passive driver. Normally you have this on the side, and there are some advantages having as a coplanar, that it's in the same plane and that it's concentric with the driver. That has some advantages for the signal. They coincide in phase, and there are actually some nice advantages which you will hear more about in the following presentation. What I will show is that we can actually design this in our software. And here is one, let me see in there. Okay. So you can see that we have the two parts. We have the driver here, and then we have the outer part there with dimensions. And these you can input directly here. Then we, maybe I should have another curve. One second. Yeah. Maybe you can see that over here, when we tune the passive driver, we tune it with adding mass. Instead of Bayes fix, where we change the port, we change the added mass with a passive speaker. So we have found a good response, and then the total mass is 41 grams. Now we know the area because that is given from the beginning, but when we look at the resonance frequency, free air resonance, we either may know that or we may know the CMS. If we have gotten the data from fine suspension, then we will know CMS and we can put it in directly there. So that is the total compliance of those two surrounds that we have here. And you can see that one surround is actually very wide and the other smaller. All this you can calculate and balance in fine suspension. Or you can buy a finished driver, of course. So now we can design this passive radiator directly here. And as I mentioned, those compliances in the passive radiator, we are interested in having a large area of the passive driver because then the excursion is limited. But on the other hand, we don't want the speaker to be too big. So if we can make the surround smaller, that would be nice. And that's precisely what we have done here. If you look at this, say, half roll surround, it's not a half circle. It's much higher than that. And it's using this template, which is actually kind of triangular. It's not the easiest design, but we have managed to make a very nice characteristic of it. It's absolutely nice and flat here, and then stiffens up pretty well when we exceed our operating range. So this ended up being a very good design that did not use too much space in this direction. We can do it for both surrounds, but here's only shown one. And here we have now our final response. That's the full dashed line here. There are also a number of other curves. This curve here is using, this button says boosted SPL, and this is the potential we can get with boosting with DSP. And it's very nice that we can just have a button and say, what can we get? What response can we get from this? And this is quite a nice base extension there. The two curves here, this curve is excursion of the driver itself, and this dashed line is Xmax. So that goes up to just a little about Xmax at low frequency, whereas the passive driver goes much higher, almost up to 10 millimeter. But at the same time, we decide to build in filters. I will show that in a second here. Because from here we can deduct the voltage necessary to get to Xmax at all frequencies. And that, you can imagine here, at this point here, the excursion is very low, so we can afford to boost it quite a bit to get up to Xmax here. So this potential we're going to use. And this potential we export it as a max voltage curve for all frequencies. That's the yellow curve. So we can see there's a lot of potential for boosting right here. And we don't use all the potential, we use the red line here. But still we have moved from this pink response up to the white. So considerably improvement in base there with the boost, which still is safe without exceeding Xmax. So we can expect to have controlled distortion. And note the word controlled because it's not below 1%, it's higher. But it's still acceptable in most cases. But anyway, many modern speakers are designed this way. So the potential with the boost is great, and we can control all this in fine DSP and get the data fine box. So the Dynaberg speaker design can be used. You can actually hear it in our booth. The funny thing is that since the main driver is small in diameter, it can work down to a low frequency in a small box. But then the larger passive radiator will help it at the low frequencies, as we have just seen. So it is a nice combination. It works well in many cases. And we have a paper about this, and there will be the following presentation explaining more about, let's say, the acoustical part of this. So that's almost what I wanted to say. I can just show one little thing, is that we have, for speaker design, we now have these three programs that we have actually used today, starting with fine suspension, fine motor, and fine cone. They are all finite element, but used in different ways. So these can be used to design and optimize speaker drivers. And that is the end of my presentation. Thank you. Any more quick questions? Yeah.
Where can we see the demo? Where?
In our booth, it's just besides Kurt Müller. I can't remember the name, the number. Okay, thank you. Okay, thank you.